In this video, we're going to talk about Chapter 1 Introduction and 1.1 Notes. The topics are data analysis, making sense of data, and analyzing categorical data. The first two I can statements are I can identify the individuals and variables in a data set, and I can classify variables as categorical or quantitative. First, individuals and variables in a set of data. Two very basic terms when you're looking at a set of data. First, individuals they're the objects or people or things being measured. Variables are the measurements we are taking about those individuals. Now, variables come in two different types. The first type is categorical. You may previously know it as qualitative. All this information is non-numerical. So colors, favorite teams, foods, stuff that can't be put on a number line. The other type is a quantitative. And this is actually strictly numerical information. If you have trouble remembering this, qualitative, quantitative. Qualitative, root word quality, like the qualities of somebody. They can't be described with numbers. Quantitative, quantities, that's a numerical term, quantity. We're going to skip the example from the book. We did this in class, but essentially it gives you a table with a bunch of information about 10 Canadian students, and it turns out the Canadian students are the individuals, and the variables being measured are the gender, wrist size, number of languages spoken, and so on. We're going to move on to analyzing categorical data. I can display categorical data with a bar graph and decide if it would be appropriate to make a pie chart. And second, I can identify what makes some graphs of categorical data deceptive. Keyword there, deceptive. With data, everyone could have the same data, but we could all present it in different ways. Certain people present data in a way to make it advantageous for themselves, so they're trying to sell a product. And we're going to teach you how to look out for those things, especially in graphs. First, describing categorical data. Discuss relative sizes and use the mode when describing. We talk about mean, median, and mode in earlier math classes, and it's important to know all three and when to use all three. Mode is when you're going to use that only in categorical data because you can't find the mean of colors or you can't find the median of your favorite sports team. That doesn't make a whole lot of sense. You can't put that on a number line and average those numbers. So categorical data, you strictly use the mode when describing the data set. Types of displays, you got two main types. Bar graphs. These are most often used to display categorical data. That doesn't mean that bar graphs are only for categorical data. It just means they mainly graph categorical data. You can use quantitative data for this. Often easier to make and read. Probably the most basic type of graph that someone can make. Just a real quick sketch. Bar graphs are the easiest one, most likely. can display frequency. That's just like your raw score, just the raw count. Or relative frequency. Each of these has its place. Let's erase that word. Relative frequency, remember, is in relation to the whole. So we're talking about percentages here. Out of 100%, how much is this category? That's your relative frequency. Well, your frequency is just going to be a raw count of what happened, or how many people like the Detroit Lions. Pie charts, only used to compare a category's relation to the whole. So that means you're going to use percentages. And that means you must use relative frequency. If you don't have relative frequency, you can't really use a pie chart. The circle doesn't make a whole lot of sense when you have those raw numbers in there. However, it doesn't mean you can't convert those raw numbers into a relative frequency score and make your own. Some data will be already set up for a pie chart, and some you'll have to convert yourself. Let's move on to deceptive graphs. We have a graph here showing massive increase in house prices this year. It's got an exclamation point. The word massive is there. They got an average house price. They got this column in green, much shorter than the column in orange, but this is deceptive. Couple of reasons. You have first, this y-axis starts at 79,000. All y-axes should start at 0. There's a reason for that. This is the reason right here. We are showing a huge jump from the green to the orange, when in fact from 80,000 to 82,000 is actually only 2,000, in this case pounds, British pounds. But it looks so much bigger. It looks like we can fit 3 of these green things, or columns, into the one orange. So it's trying to show there's a bigger increase than there actually is. So this is going to be an advantage for someone. I'm not exactly sure who, but somebody is taking advantage of this graph. Now, it would be okay if you were to start a graph at 0 and then show a little break, and to let people know, like, hey, I jumped ahead here, just to give you a heads up. They didn't do that at all in this graph. Be wary of any y-axis that's been shortened up like this to show a dramatic increase. It can be useful at times, but in this case, it's clearly deceptive, because if you look at the title, it says massive increase in house prices this year. So they are trying to use the word massive pretty loosely here, and that's not okay. Okay, next section. I can calculate and display the marginal distribution of a categorical variable from a two-way table. I can calculate and display the conditional distribution of a categorical variable from a particular value of the other categorical variable in a two-way table. And I can describe the association between two categorical variables by comparing appropriate conditional distributions. So, looking at two-way tables, can you look at the data? Can you manipulate or can you create percentages to form an argument for or against something? That's essentially what's going on here. This example is Titanic passengers. It's broken down by class, crew, and then whether they survived or whether they died on the sinking ship. So we have 4 questions here, and then an argument to be made, and we could talk about ways to argue for or against that. First, what percent of first class passengers died? So the of first class, that's your whole comparison there. So first class you're going to focus on here. The total is 325. That's going to be your denominator. That's your relation to the whole, 325. Passengers that died in first class, that's going to be 122. And approximating that percentage for you, you get 37.5%. So approximately 37.5% of passengers died from first class. What percent of third class passengers died? Same question, they just swapped out third or first with third. This denominator changes now to 706. You'll correctly note that third class was much larger than first class. The people that died, 528. That's approximately 74.8%. Third question, what percent of the total passengers died? Total passengers is 2,201. And the percent that died, you're going to take your 1,490 and divide it by your 2,201, and you're going to get approximately 67.7%. Last question, what percent of the survivors were in the first class? So survivors, of the survivors, that's your new denominator. Survivors ended up being 711 up here. So what percent of that 711 is going to be a set of first class people? So that's 203. So 203 out of 711, approximately 28.6%. So looking at these just now, if you compare the first two answers, first class passengers died, third class passengers died, one's considerably larger than the other one. Not only the raw score, because of, there's more people in third class, so it makes sense that more people would die, but the percentage, only 37% or 38% roughly of people died in first class, while 3/4 of people in third class died. It's a big difference in percentage there. Also, if you look at the total percentage of passengers died, 75% for third class right here is well above the total or the average death rate for the entire ship, while first class, 37.5, is much less than the entire ship. Here's a suggestion made by historians. First class passengers received special treatment in boarding the lifeboats, while some other passengers were prevented from doing so, especially third class passengers. Is there any truth to this? Use data to support your answer. So you can look at the data here and try and make an argument. What I would not try and do is try and use different information from, like, let's say, a fictional film to inform your answer. Let's only use the data here. So what you could do for the argument for this suggestion made by historians. First of all, the percent death rate is higher for third class than first class. This could be in response to someone saying, hey, there's more third class passengers, so obviously more of them are going to die. The problem with that is the percentage is much higher. So when you take both of them and you make them into percentage out of 100, now you can compare the two groups even though they have different numbers of people. One had 706 people, one had 325. You could say, well, I can't compare those two because there's too big of a difference. But if you compare them through percentages, that allows you to say, hey, third class, 75% died. First class, only 38% died. It looks like the first class passengers had an advantage here. Another argument you could say after that is more people survived in first class. More people survived in first class than third class, even though there was over twice as many third class passengers. So more people survived in first class than third class, even though there are over twice as many people in third class. So think about this. You had 203 first class passengers survive, and you had 178 third class passengers. Just by raw score, first class passengers out-survived third class, even though they had less than half the passengers. So right there, that should show you that the first class had some kind of advantage here in order to have a way higher success rate of surviving the sinking ship. Now, you could make the argument that the first class had an advantage baked in because they were closest to the deck. Third class had to go up a few stairs. Maybe. Well, we don't know the exact data on that. It's on the table here. Maybe you could make a side argument about that. But this would be a couple statements made and for this argument altogether. It's not so much about one side or the other. It's how strong is your argument. A lot of people can say, "Oh, I support," or I'm not supporting this statement. But people a lot of times fail to come up with reasons why. And a big skill that you're going to learn about in this class is creating an argument and then using data to back up that argument. And this is a couple of examples of how you could do that. The last section of the notes here, we're going to talk about contingency tables. I'm going to show you this table here and go over what joint, conditional, and marginal distributions are. And then I'm going to show you the segmented bar graph that goes with this to kind of show you how we compare across groups of different number raw scores with relative frequency. So first, let's talk about marginal distributions right here. Marginal distributions are distributions across a variable. You'll notice that the two red arrows are pointing to the column and the row for the totals across the two variables for eye color and hair color. So across eye color, your marginal distribution would be taking each of these numbers, 220, 215, 93, 64, and dividing them by the total, 592, and you get a percentage for each of those. Same with the hair color across the bottom here. You do 108, 286, 71, 127, all divide each of those numbers by 592, and you get a percentage. That's your marginal distribution across a variable. More specifically, in the green, let's change colors here. The green, it's the distribution of the conditional distributions, more specific to one aspect of the variable. So not the entire band of hair color, but just blondes. That's a conditional distribution. You do one segment right here of the entire spectrum of hair color. So 7 divided by 127, 94 divided by 127, 10 divided by 127, and so on. You don't go all the way back to 592. You're not going to use that number in a conditional distribution. A joint distribution is like the intersection of two things. For example, in blue here, brunette. Let's use appropriate color. I'm not going to use green, I'm going to use blue. Brunette and blue eyes. That's your joint distribution. You can do that out of the total here, 592. Very specific number because you're choosing two specific parts of the variable, hair color and then eye color. So those are your three types of distributions. We're going to move to the segmented bar graph now. Kind of show you how it looks when you actually make a bar graph. So this is not in color, but I tried to use a different pattern for each group. And the idea behind this is going to show you what big trends are happening, because raw numbers are kind of hard to look at. Unless you're a certain kind of person that looking at just numbers. The majority of people are visual people. They need to look at a graph. So if you look at this graph here, you'll notice that the hash marks here, this group, it's kind of going down here. And then it gets to the very end, the blonde. Look at the blonde column. It's very much different than the other three columns, and it shows you that middle section there, that blue, the blue eyes go with blonde quite a bit. It's the majority of the population there. The other three columns, blonde, the diagonals going from bottom left, top right, those aren't really a big subsection. It's a sizable group, but once you get to the blonde, it's so much bigger than the rest of the groups. That may have been hard to see by looking at just the numbers. Also, you'll notice that the bottom category, the brown eyes, best go with the black hair. It's kind of sizable in the brunettes and the reds hair colors, but the black hair color, the brown eyes, is almost as big as the blue eyes for the blonde. Also, could have been difficult to see. But the big idea here is that the last column is just so much different from the rest of the three, and it would have been hard to look at that without looking at the the graph of it. The numbers may have been hard to see. How we made this graph, you'll notice that all four columns out of 100%, and that was done on purpose so we can compare across different raw numbers. Relative frequency helps us do that. The table shows different totals. We have 108, 286, 71, 127. It's hard to compare numbers when they're all the same. When they're all 100%, it's so much easier. You can tell, keeping all the columns the same height, it's no big deal. I can easily say, hey, blonde, the blue eye column, that section is so much bigger than the rest of the columns. It makes it easier just for to look at. This column the segmented bar graph here takes a bit of time, making all the percentages. But you will be able to use this and draw a conclusion from it. So if I were to ask, what conclusions can you draw from this graph? You'd have to say something about the blonde hair, blue eyes. It's so much different than the rest of the graph. You could also say something about the brown eyes and black hair as well. You could also mention, that the very top square, the green eyes, is by far the smallest in each group. It looks like. I know that's constant. That's something notable. When something is constant across four bar graphs, it's pretty notable. You need to write something down about that. You have to go past the basics of the graph when you talk about it. Don't tell me that there's 4 bar graphs, they're all out of 100%. That's not telling me anything about the data. The whole point of the graph is for you guys to conclude about something about the data. So, in these notes, we've talked about different types of variables about individuals: categorical, quantitative, or categorical, qualitative, and then quantitative as well. Is it non-numerical? Is it numerical? We talked about deceptive graphs, what to look for there. Make sure you look at the y-axis. It's got to start at 0. Look for any headlines that are misleading. The words don't, really fit the graph. Bar graphs and pie charts. Bar graphs can be used for qualitative or quantitative, mostly for qualitative. Pie charts are only used if they have a relative frequency. You can't use raw scores for pie graphs. It must be 100% the total and split up into different pie pieces. We talked about how to find different distributions using a two-way table. And finally, the most difficult part of that is creating an argument for or against a suggestion. We talked about the Titanic suggestion made by historians. They were talking about how first-class passengers made it through easier because they had favored treatment. And we had to create an argument for that or against that. We chose to say, yes, we agreed based on the percentages. And finally, we talked about this last segmented bar graph, making sure that you guys understand how to use the bar graph to make a statement about the data and how to actually use it appropriately rather than maybe a superficial way. Again, most people like looking at the bar graph over the raw data set. Those are just numbers to people usually. It's hard to tell, but a bar graph really makes it easy for everyone to look at.